In our previous lesson, we talked about graphs of a number of different polynomial functions. In this lesson, I'd like to spend a good bit of time talking about how we combine polynomial functions to make new ones using operations like addition, subtraction, multiplication, division, and something called composition. We spent some time in one of the review lessons for this course discussing some of these ideas, but I want to take them further in this lesson. First, let's talk about adding polynomials. You've already seen everything you need to know about how to add two polynomials. Basically, you just combine like terms. So let me suggest you try this example yourself and see how you do before we come back together. Simplify 7x to the fourth plus 5x squared minus 2x plus 3 plus 8x to the fourth minus 9x cubed plus 15x squared plus 12x plus 27. Okay, let's see if I got the same answer that you did. The key here is that we put together the like terms. So just be careful to combine the right terms together. That's the key. I see a 7x to the fourth plus an 8x to the fourth. That gives me 15x to the fourth. I'm going to have a negative 9x cubed because it has no term that I want to combine with, so that's no problem. I have a 5x squared and a 15x squared. Those can be combined to give me 20x squared. There's a negative 2x plus a 12x. Those can be combined to give me 10x. And lastly, the constants 3 and 27 can be added together to give me 30. So the sum in this example is 15x to the fourth minus 9x cubed plus 20x squared plus 10x plus 30. Now, notice something really interesting here. We started with two polynomials of degree 4, or two quartic polynomials, and the final answer turned out to be another quartic polynomial. And here's an interesting question. Is that always going to happen? Well, let's look at one more example of addition to see if we can pick up on the general pattern. Try simplifying the following expression. Simplify 5x to the fourth plus 18x squared minus 10 plus 6x cubed plus 7x squared plus 8x. Again, we're combining the like terms, and when we do so, we get 5x to the fourth plus 6x cubed plus 25x squared plus 8x minus 10. Was that the answer you got? Well, notice that in this example, I started with a polynomial of degree 4, that's a quartic polynomial, and another polynomial that had degree 3, which was a cubic polynomial. And the answer turned out to be a quartic polynomial as well. Now, can you see the pattern? Well, here it is. If f of x is a polynomial of degree, let's say, a, and g of x is a polynomial of degree b, then f of x plus g of x is also a polynomial, and its degree will be at most the larger of the two numbers a and b. In fact, most often the degree of f of x plus g of x will be exactly equal to the larger of either a or b. So for example, when we started with the two polynomials of degree 4, we ended up with another polynomial of degree 4. And when we started with a polynomial of degree 4 and another polynomial of degree 3, the final answer had degree 4, because 4 is larger than 3. The only time that the degree of f of x plus g of x is not going to be the larger of the two degrees with which we started is when a equals b, and the leading coefficient of one of those polynomials is the negative of the leading coefficient of the other. For example, if you started with f of x equals 8x to the fourth plus 5x, and g of x equals negative 8x to the fourth plus 7x cubed minus 2, then f of x plus g of x would be 7x cubed plus 5x minus 2, and the degree would have actually gone down. It would have gone from being degree 4 in the original two polynomials to a degree 3 for the sum. And that's because the terms 8x to the fourth and negative 8x to the fourth actually canceled one another out when we did the addition. Now, what about subtracting two polynomial functions? There's addition and there's subtraction. Well, to combine the like terms in these subtraction problems is identical to doing them with the addition, but you have to keep an eye on distributing the minus sign correctly. Anytime you subtract, it's very, very important that you make sure you distribute that minus sign. So let's be careful as we walk through a couple of examples of subtraction just to make sure we combine the terms correctly. So why don't you try this one yourself first? Simplify 17x to the fourth plus 5x squared minus 2x plus 3 minus the polynomial 8x to the fourth minus 9x cubed plus 15x squared plus 12x plus 27. Okay, we have to be careful when we distribute that minus sign that's in between the two polynomials. So my first suggestion would be to just do the distribution as if you had to do it first. So just take that minus sign and drive it through the second polynomial. And when you do that distribution, you'll get 17x to the fourth plus 5x squared minus 2x plus 3 minus 8x to the fourth plus 9x cubed minus 15x squared minus 12x minus 27. Now, there's no doubt about the signs of each term now because I've taken care of everything by doing the distribution. And now I just have to combine the like terms as if I was doing the addition problem or addition problems that we've done a few moments ago. So here we go. You have 17x to the fourth minus another 8x to the fourth, and that's going to be 9x to the fourth. Then there was a 9x cubed by itself. There were no other x cubes. No problem. Just keep the 9x cubed as it is. 5x squared minus 15x squared is going to give you negative 10x squared. Then you have negative 2x minus 12x, which is negative 14x. And lastly, the constants, 3 minus 27 is negative 24. So our final answer then is 9x to the fourth plus 9x cubed minus 10x squared minus 14x minus 24. Notice again that the degree of this result is not any larger than the degrees of the polynomials with which we started. That's very important. It's going to have a very similar flavor to the degrees that we found in the addition problems and the discussion that we had a few minutes ago with those problems. Now, let's look at one more subtraction problem quickly, and I'm going to suggest you try it yourself and be careful with the distribution of that minus sign. So here's the problem. Take x cubed plus x squared plus 1 minus the polynomial x cubed minus 5x squared plus 7x. Again, this is the same as x cubed plus x squared plus 1 minus x cubed plus 5x squared minus 7x. And this then combines, now that we've done that distribution of the minus sign, to 6x squared minus 7x plus 1 once you write it all in standard form. Is that what you got? That's good if you did. Now, notice that in the first subtraction example, we started with two polynomials of degree 4, and the final answer was another polynomial of degree 4. In this second example, we started with two cubic polynomials and ended up with a quadratic trinomial. So the degree of the final answer after you've done a subtraction of two polynomials cannot be any larger than the largest degree with which we started. But that degree of the answer might be smaller, again, due to cancellation of the terms of highest degree. When that happens, the degree of the final answer is actually able to go down. Now, the next usual operation to discuss is multiplication. So I suggest we do a few multiplications of polynomials now, just to make sure we've got that operation down. I'm going to start with a quick example of multiplying one polynomial by a monomial. Remember what a monomial is? It's a one-term polynomial. So let's see if you can do this as we expand or multiply out the following product, or the following two polynomials being multiplied together. Here they are. I'm going to take 3x squared, that's the monomial, and multiply it by 6x cubed minus 4x squared plus 7. Now, how do we do this kind of problem? Well, it's really just a big distributive property problem. It's just that it's kind of expanded because of the size of the polynomial that I have inside those parentheses. But it's very doable once you get used to this idea of just distributing the monomial out in front all the way through the other polynomial. So once you do that distribution, you're going to have 3x squared times the 6x cubed plus 3x squared times the negative 4x squared plus 3x squared times 7. You just have to keep taking that 3x squared times all the other terms. And when you get that and you multiply everything out and simplify, you're going to have 18x to the 5th minus 12x to the 4th plus 21x squared. And that, of course, uses some of the laws of exponents that we've talked about in the past. And you're done. And if you got that answer, then you've done a perfect job. Now, one quick comment before I go on to the next example about multiplication. Now let's talk about degrees. You might be getting tired of this philosophical conversation about these degrees, but I want you to see this because it helps us with critical thinking. If you get an answer that doesn't match up with these comments we're making about degrees, then it could tell you very quickly that you've done something wrong. Notice in this problem that the degree of the result we got after the multiplication is exactly the sum of the degrees of the two polynomials with which we started. We started with a 3x squared and we started with 6x cubed minus 4x squared plus 7. Look at the two degrees. The degree of the first polynomial was 2 and the degree of the second polynomial was 3. And notice that in the final answer, the degree was 2 plus 3, or 5. So multiplication of polynomials is a way to build polynomials of larger degree from polynomials with smaller degrees. And that's a nice idea. So addition and subtraction weren't really getting us to bigger polynomials or polynomials of bigger degree, if you will. But multiplication does. It actually takes two smaller degree polynomials and after multiplying together gives us a bigger degree polynomial, and that's nice. Now, I'd like to look at a second example of multiplication of two polynomials, and this time we're going to multiply a binomial with a trinomial. That means we're going to multiply a two-term polynomial with a three-term polynomial. And this acts a lot like FOIL, if you've heard that in the past, but it's a bit more involved. So let's do the following example. I want us to expand or multiply out x squared minus 7 times x cubed plus 9x squared minus 5x. Now the key here, which is a lot like the FOIL method when multiplying out two binomial expressions, is to make sure that every term in the first set of parentheses is multiplied with every term in the other set of parentheses. So the x squared must be multiplied with each of the three terms in the trinomial, and the 7 must be multiplied with each of the three terms in the trinomial. So you'll actually have 6 different multiplications to perform. Once those are done, you can then combine the like terms to get the final answer. So, given those comments, let me suggest that you try that expansion, that multiplication, and the combining that happens after. So, let me remind you of the problem again. It's x squared minus 7 times x cubed plus 9x squared minus 5x. Try it yourself. Okay, here's how I would do it. I would actually start by multiplying the x squared through all the terms that are in the trinomial. And when I do that, I'll have x squared times x cubed plus x squared times 9x squared plus x squared times negative 5x. Okay, that'll be the start there. And then I have to do minus 7 times all the terms. And I'll have minus 7 times x cubed minus 7 times 9x squared minus 7 times negative 5x. Okay, so now I have my 6 terms. And now I can start combining or doing the multiplications, if you will, in each of those 6 and simplifying those. And when I do that, I'll have x to the 5th plus 9x to the 4th minus 5x squared, minus 5x cubed minus 7x cubed minus 63x squared plus 35x. And when I combine those like terms together, I'm going to have x to the 5th plus 9x to the 4th minus 12x cubed minus 63x squared plus 35x. Now notice again that the degree of this final answer is 5, and it's equal to the sum of the degrees of the two polynomials that we started with, which were 2 and 3. Now, these kinds of problems deserve lots of practice. So let's look at one more example. And in this case, it's going to be a 3-term polynomial or a trinomial with another 3-term polynomial, another trinomial. So let's expand the following. X squared plus 2x plus 3 times x squared minus 4x minus 6. Now, again, each term in the first trinomial has to be multiplied with each term in the other. So that's going to give me actually 9 different terms before we combine the like terms. So let's do it. I'm going to have x squared times x squared plus x squared times negative 4x plus x squared times negative 6 plus 2x times x squared plus 2x times negative 4x plus 2x times negative 6 plus 3 times x squared plus 3 times negative 4x plus 3 times negative 6. So every term in the one set of parentheses is now multiplied with every term in the other set of parentheses. And that gives me x to the 4th minus 4x cubed minus 6x squared plus 2x cubed minus 8x squared minus 12x plus 3x squared minus 12x minus 18. And when I combine all the like terms, I get x to the 4th minus 2x cubed minus 11x squared minus 24x minus 18. All right, I'd like to move on now to another operation. And in this case, we're going to look at division. We've looked at addition, and we've looked at subtraction, and we've looked at multiplication. And now I'd like to move on to the next operation, which is actually division. Now, in the case of long division of two polynomials, you're actually not necessarily going to end up with a new polynomial. Because, as I've already said, when you have one polynomial divided by another, you actually might not end up with a polynomial function. So, let's move on now to some examples of division. They can get a bit messier compared to some of the others. And sometimes you'll even end up with a remainder when one of the polynomials doesn't perfectly divide the other polynomial. But we still need to be able to do this polynomial division, whether we have remainders or not. So let's look at a couple of examples of polynomial division just to make sure we know how to do this. This, by the way, is very helpful when we're thinking about factoring, and I'll try to talk about that in a second. Here's the first example. Simplify x squared plus 10x plus 21 divided by x plus 3. Well, I want to do this like a long division problem, just like you would with polynomials. So we're going to draw that long division symbol, put the x squared plus 10x plus 21 underneath that symbol, and put the x plus 3 out in front as the divisor. And now what I want to know is, how many times does x go into the x squared? Okay, so what would I need to multiply x by to give me x squared? And the answer is x, because x times x is x squared. And now I'm going to ask myself, what is x plus 3 times x? And I'm going to write that just underneath the x squared plus 10x plus 21. And x plus 3 times x is the same as x squared plus 3x. So I put that underneath, and now I do, just like with long division of numbers, I subtract. X squared minus x squared is 0, it's gone. 10x minus 3x is 7x. Okay, and now what would you do with long division of numbers? You would next drop the 21 down, and you would have 7x plus 21. And now you ask yourself, just like with long division of numbers, how many times does that x that's up in the divisor go into 7x? And the answer is, it goes in 7 times. And when you multiply x plus 3 times the 7, you're going to have 7x plus 21. And now when you do the subtraction as usual, you're going to get 0, because 7x plus 21 minus 7x plus 21, and that's minus the quantity 7x plus 21, is just going to be 0. So your final answer is x plus 7 with 0 remainder. So in that case, we divided a quadratic polynomial by a linear polynomial, and the answer turned out to be just another linear polynomial. Now that's not typical. It turns out that sometimes you'll have no remainder. You'll have 0 remainder, as we did a moment ago. But that's because the two linear pieces were actually factors of the quadratic piece. We could have actually factored the quadratic polynomial into those two linear pieces. In other cases, you're going to have a remainder that's not 0. And in this case, I think we'll see that. So let's take the following example and again do the long division. I want us to simplify x cubed minus 6x squared plus 19x minus 4 divided by x minus 2. Why don't you try it yourself and see what you get? Now, you might have noticed that that didn't come out quite as neatly, right? There's a bit of a remainder, but that's okay. Let's walk through it together, step by step, and see if we can actually see what our final answer is. So I'm going to draw a big long division symbol. Underneath it, I'm going to write x cubed minus 6x squared plus 19x minus 4. On the outside where the divisor goes, I'm going to put the x minus 2. And now I'm going to ask, how many times does the x in the divisor go into the x cubed? And the answer is x squared times, because x squared times x is x cubed. And so now I have the x minus 2 times that x squared. I write that x squared up above the division symbol. And I multiply the x minus 2 times the x squared. And I'm going to have x cubed minus 2x squared. Now I must subtract that term. And remember, I'm subtracting the x cubed, and I'm also subtracting negative 2x squared, which is the same as adding positive 2x squared. When I do that subtraction, I'm going to have 0x cubed, the x cubes will cancel each other, minus 4x squared. That's from a negative 6x squared plus 2x squared. I have negative 4x squared. And now I can drop down the next piece, the next term, which is a plus 19x. And now I ask the same question. How many times is that x minus 2 going to go into the negative 4x squared plus 19x? Well, I need to really simplify that problem by asking, how many times will x go into negative 4x squared? That's really the question. And the thing I need to multiply the x by to get negative 4x squared back is negative 4x. So I'm going to put a negative 4x on the top, just after the x squared. And now I'm going to ask, what is negative 4x times the x minus 2? And when I do that, I'm going to have negative 4x squared plus 8x. Negative 4x times negative 2 is plus 8x. And now I have to subtract all of that. And again, I've got to distribute that minus sign carefully as I go. Negative 4x squared minus the other negative 4x squared is 0. 19x minus 8x is 11x. So now I have an 11x there, and now I just do the same thing again, drop the minus 4. So now I have 11x minus 4. And I need to ask myself, how does the x minus 2 go into 11x minus 4? More importantly, how many times does x go into 11x? And x goes into 11x 11 times. So I put a plus 11 on top, and I have to multiply that 11 times the x minus 2. When I do that, I get 11x minus 22, and I must subtract that. And again, I've got to be careful. That means I've got 11x minus 4 minus 11x plus 22 when I distribute that minus sign. And the 11x minus 11x is 0. Minus 4 plus 22 is a plus 18. And now I'm done. And the reason I'm done is because 18 doesn't have any x's in it. Its degree, if you will, is smaller than the degree of x minus 2. So I quit. And I know that my final answer then is x squared minus 4x plus 11 with a remainder of 18. And by the way, because that remainder is not 0, it means that I know that x minus 2 does not evenly divide or perfectly divide the original numerator, the first function, x cubed minus 6x squared plus 19x minus 4. And I can say that another way. It means, since I have that non-zero remainder, it means that if I took the function x cubed minus 6x squared plus 19x minus 4, divide that by x minus 2, I definitely would not have a polynomial. I would have a much more complicated function. Okay, let's look at another example of this long division very quickly. Let's simplify x cubed minus 8x squared plus 7 divided by x minus 1. Now I wanted to do this example because I'm actually missing a term. If you look at the function we're going to divide, It has no x term, if you will. The x cubed minus 8x squared plus 7 is missing an x term. What do? Well, you just simply insert it with a 0 in front. And that means when you're ready to draw everything, you're going to have an x cubed minus 8x squared plus 0x plus 7 underneath the division symbol, and you're going to have the x minus 1 outside as the divisor. Okay? So once you've written that, let me ask you this. Try it yourself. Try dividing that x minus 1 into x cubed minus 8x squared plus 0x plus 7 and see what you do. Okay, let's come together and see how we worked it out. We're going to ask ourselves first, how many times does the x go into x cubed? It needs an x squared. And once I multiply the x minus 1 times that x squared that I've written on top, I'm going to have x cubed minus x squared. Doing the subtraction gives me negative 7x squared, and then I'm going to have to drop a plus 0x. And yes, drop it. You really need to do that. Now, the x minus 1 then goes into a negative 7x squared. Well, it goes in negative 7x times. Again, only focusing on the x going into the negative 7x squared. So I put a minus 7x on top. Multiplying by that minus 7x gives me negative 7x squared plus 7x when I multiply the negative 7x times an x minus 1. Subtraction, again, remembering to distribute the minus sign, gives me negative 7x, drop the 7. I have negative 7x plus 7 at that point, and I have to ask myself, how many times does the x in the divisor go into negative 7x? And it goes in negative 7 times. Put that negative 7 on top, multiply that negative 7 times an x minus 1, and I get negative 7x plus 7. Watching out for my minus signs again. Subtraction gives me 0. And that's cool because it means that the x minus 1 evenly divides, or is a factor of, x cubed minus 8x squared plus 7. And the final answer then, when I do that division, is actually a nice polynomial. It's x squared minus 7x minus 7. And again, you're going to see a lot of remainders that are not 0. In this case, we actually did have a remainder of 0. Most of the time, if you just write down two polynomials, you're going to see a non-zero remainder. Now, these division problems can get kind of messy, but I'd like to look at one more of them where we divide by a quadratic function rather than a linear one. And so let's look at the following problem. Let's divide x to the fourth plus 9x cubed plus 2x by x squared plus 2x plus 1. Now, if you remember to add in those terms that we're missing by putting a 0 in front of them, you're going to have x to the fourth plus 9x cubed plus 0x squared plus 2x plus 0 underneath the division symbol. And in the divisor area, you're going to have an x squared plus 2x plus 1. Now, you ask the same question. How many times does the x squared go into the x to the fourth? And it goes in x squared times, because x squared times x squared is x to the fourth. Multiplying that x squared by the divisor, x squared plus 2x plus 1, gives you x to the fourth plus 2x cubed plus an x squared. And now you subtract. It's the same as usual. And the x to the fourths cancel, and you're left with 7x cubed minus x squared plus 2x after you do the drop down of the 2x. And now, how many times does x squared go into 7x cubed? The answer is plus 7x times. Put that on top. Multiply the 7x times the x squared plus 2x plus 1, and you'll have 7x cubed plus 14x squared plus 7x. Do the subtraction, remembering to distribute the minus sign, and you'll have minus 15x squared minus a 5x, and now you drop down the 0, if you will, that's up there inside the original function. And now you ask yourself, how many times does x squared go into negative 15x squared? Answer, negative 15 times. Multiplying the negative 15 times the x squared plus 2x plus 1 gives you negative 15x squared minus 30x minus 15. Subtract, being very careful of those minus signs, and you're left with 25x plus 15. And you stop there because the degree of 25x plus 15 is actually smaller than the degree of x squared plus 2x plus 1, which was your divisor. So my final answer is x squared plus 7x minus 15 with a remainder of 25x plus 15. Now, we've talked about enough about division at this point. We've shown 3 or 4 examples of long division of polynomials. I'd like to close with one more operation today, and that's composition. Now, we've talked about composition of 2 functions already in some of our earlier lessons. Let me just make this quick comment, and that is that when you compose 2 polynomials, you get a new polynomial, which is great. And when you do this composition, you have to be a little careful. It's a bit trickier than the other operations. So let me do a couple of examples here quickly. So the first example is the following. Let's let f of x equal x cubed plus 3x minus 1 and g of x equal x squared minus 2. I want to determine f of g of x and g of f of x. Now f of g of x is like plugging g of x into f. So when I do that, I'm going to have the following. F of g of x equals f of x squared minus 2. I've just plopped the g of x into the function f. And that's the same as x squared minus 2 cubed plus 3 times x squared minus 2 minus 1. Now, I've got to expand the x squared minus 2 cubed. And this is similar to just taking something like t minus 2 and cubing it. All it means is you have to multiply it by itself 3 times. So you'll have the following. X squared minus 2 cubed equals x squared minus 2 times x squared minus 2 times x squared minus 2. And when you multiply that out, the first 2 terms give you x to the 4th minus 4x squared plus 4 times x squared minus 2, which is x to the 6th minus 4x to the 4th plus 4x squared minus 2x to the 4th plus 8x squared minus 8 by doing the distribution, which is x to the 6th minus 6x to the 4th plus 12x squared minus 8. And that means that this composition, once you do all of the work together, is going to be x to the 6th minus 6x to the 4th plus 15x squared minus 15. And now let's do the composition in reverse order. Let's find g of f of x when f of x is x cubed plus 3x minus 1 and g of x is x squared minus 2. So g of f of x now takes f and plugs it into g, which means I want g of x cubed plus 3x minus 1, which is just x cubed plus 3x minus 1 squared minus 2, because I've plugged f into g. So I want x cubed plus 3x minus 1 times x cubed plus 3x minus 1 minus 2. And when I do all that distribution that we've talked about earlier and simplify, we'll have x to the 6th plus 6x to the 4th minus 2x cubed plus 9x squared minus 6x minus 1. I know it's a lot of pieces, but it really works out in the long run, and you get this nice, clean function. It's a little long, but it's still a polynomial. And notice, f of g of x here is not equal to g of f of x. I've mentioned this before. When you do composition in either order, you often get a very, very different answer. Well, we've talked about operations of addition, subtraction, multiplication, division, and now composition today. I hope you've enjoyed this work. It feels very algebra-like, doesn't it? We'll continue to use these operations in our future lessons, and next time we're going to come back to factoring. I'll see you then.